Okay, so now let's talk about a different way to calculate eigenvalues for and eigenvectors for graphs, which involves what are called equitable partitions. Okay, so we did some graphs in the previous part, but let's say you have graphs that maybe look like this or like this, or maybe even the Peterson graph have some kind of regularity or symmetry in them. How can you use that to get to get a handle on, to figure out the eigenvalues and the eigenvectors? So one method is this method of equitable partition. So let me define it first. So definition. So let's say we have a graph with vertex at V. And so we're talking about partition. So let's say we have a partition pi into vertices x1, xm. So I put the dot there to signify that these parts x1, x2, xm are not empty and they're disjoint, and together they form the vertex at V, is called equitable if the following happens. There exist some numbers bij for I and j between 1 and m. So the m is the m from here, the number of parts, okay? Such that the condition is the following. For any I, and for any, let me put it this way. For any ij in the set 1 to m, and for any x in the set xi, the number of neighbors, so let me call nx is the set of neighbors of x, the set of neighbors of x that live in xj equals this number bij. So let me draw a picture so that you can see what happens. So in this graph, we have this partition, this subsets of vertices. So you have x1 somewhere, x2 somewhere, and so you will have xi somewhere and xj somewhere. Xi and I and j could be the same, but for now, let's just think about them this way. And so the condition says that you have these numbers that do not depend on the vertex x. They depend only on the partitions, on the 1, 2, 3, m, or x1, x2, xm. And so whenever you give me a vertex here, x, and you look at the neighbors, the number of neighbors that it has that live in xj, in xj, that number is this number bij. So this number is bij. And so similarly, if you give me another vertex here, let's call it z, and I look at the neighbors there in xj, the number of neighbors is also the same. They may not have the same neighbors, but they have exactly bij neighbors all the time. Okay, so that's what we mean by an equitable partition. So you have these parts, m parts, and you have these constants bij that depend just on the numbers ij between 1 and m, such that no matter how you pick the I and j, and no matter how you pick a vertex in xi, if you look at the number of neighbors of x that live in xj, that is always the same, is this number bij. So let's see some examples. Well, I mean, I'll do these examples on the top on the next page so that it's easier. So if we look at this graph here, so I will draw the partitions by just different colors. You kind of see the vertex in the middle, it's in its own class. The ones in the top they look the same, and the ones at the bottom look the same. So the parts that I could use here are the following. Let's call this x1. Let's call this one x2. And these vertices at the top, let's call them x3. Okay. And now what I want to do, one more thing, is an important parameter that's associated to this partition is it will be a matrix in which we put all these bij's, and that matrix, let me squeeze it here, the matrix B, which is formed by these bij's from I and j between 1 and m, this is called the quotient matrix of this partition. The quotient matrix of pi. Okay. So what I want us to do is to go through these three examples and write down some equitable partition and their quotient matrices. So here we have this partition, and what is the quotient matrix here? Let's say B. So again, the way you think about it is you label the entries corresponding to these parts in which we. So the first one will be x1. The next one, sorry. The next one is x2. And the last one is, I wrote x2. And the last one is x3 here. And then we write the entries corresponding to, to each of these parts. So what is the entry in the first position, x1 is, if we look inside x1, what is the degree of regularity that we see inside x1? And so that value will be 1. If we look in the position correspond x1 to x2, is for a vertex, if I pick a vertex in x1, one of these two, what's the number of neighbors they will have that live in x2? And in this case, that number will be also 1. And then from x1 to x3, we have 0, so we put 0. And now we go to x2. From x2 to x1, each vertex has exactly 2 neighbors. Inside x2, we have 0 neighbors. And from x2 to x3, we see 2 neighbors. And from x3, if we look to x1, we see 0. x3 to x2, every vertex has exactly 1 neighbor. And inside, we see 0. So that's the quotient matrix. And you can see the quotient matrix is not a symmetric matrix in general. Okay. Let's do the next one, the 3 triangles. I mean, here you can do several partitions, but one partition that is clear is that the vertex in the middle is again by itself. And then if you want, you can partition all the other vertices together into a big class x2. And in this case, this equitable partition, the quotient matrix, I'll just write it directly, will be the following. Well, you have x1 here, x1 here, you have x2 here, x2 here. So x1 to x1, there's 0. X1 to everything else, it's 6. There's 6 neighbors that a vertex in x1 has in x2. x2 to x1, each vertex has exactly 1 neighbor, and inside they have exactly 1. So that's the quotient matrix here. And let's do quickly the Peterson graph. Now, for the Peterson graph, there are several partitions, so I'll just give you two. One partition you can do is, you notice that on the inside, let's call this one x1, we have a cycle, and also on the outside, I don't know how to draw this one on the outside, like this, I don't know, it's a mess. But on the outside, we have also a cycle, x2. So the partition here, if you look at the star in the center, the x1 in the center, x1, x1, each vertex there is adjacent to two vertices in that subset, and it will be adjacent to one vertex outside. And similarly, from the outside into inside, 1 and 2. So that's one equitable partition. There is another one that you can get. Let's see if I can squeeze it here. And that one is, you take as, let me change the colors here. You take as x1 one vertex. You take as x2 the neighborhood of that vertex. This is x2. And you take as x3 whatever is left, the non-neighborhood of a vertex. That's x3. And one can check that this is also equitable partition. And we have here x1, x1, x2, x2, and x3, x3. And if we look at the entries, the vertex in x1 has exactly 3 neighbors in x2. Oh, no, that's, yeah, has 0 here, has 3 here, has 0 here. A vertex in x2 has exactly 1 neighbor in x1, has 0 neighbors in x2, and you have to check a little bit in the picture, but you can see that each vertex in x2 has 2 neighbors going down, so that gives you a 2. x3 to x1 is 0. x3 to x2 will be a 1, and here we will get a 2. Okay. All right. So anyway, there are several examples. So I hope the notion is clear. Now, what can we prove about these equitable partitions? Where are we going with this? Okay, so let's prove a first a lemma. This is very important. So again, let's assume that gamma is a graph. And assume that pi is an equitable partition of gamma with quotient matrix B. So pi, as before, is x1 union xn. Now, it turns out there's a relation between these A and B, and that involves what is called the characteristic matrix of the partition. So let me define P is the characteristic matrix of the partition pi. And this matrix can be defined for any partition. The partition doesn't have to be equitable. And what is this matrix? It's a tall matrix. So there's one column for each part of the partition. So there's x1, you go all the way to the xm. And on the rows, you are labeled as in the vertex set V. And the way you define this, this P is essentially the jth column of P equals the characteristic vector of xj. Okay, so if I were to give the example of what we have before here, this graph. And let's say these were labeled 1, 2, 3, 4, 5. And 1, 2 were our first part x1. 5 maybe was our second part x2. And 3, 4 is our third part x3. So in this situation, P would have as the first column the characteristic vector of x1. So those are vertices labeled 1 and 2. So we put a 1 and 1, and then we put a 0 everywhere else. x2 is the characteristic vector of 5. So you go 0, 0, and 1 at the end. And x3 will be 0, 0, 1, 1, 0. So that's basically what P is. Okay. So then, but what we'll prove here, it's a general result. We have an equitable partition. We have the matrix A, adjacency matrix A of the big graph. We have this quotient matrix B, and we have this characteristic matrix which keeps track of the parts in the partition. So what we'll prove is that then, one, this is the most important result, A times P equals P times B. So the way you can think about it, A is a big matrix. So it's N, it's V by V, V is large, N. And then P is kind of a tall matrix. So it has M here and it has B here. And so this product will equal this tall matrix times a small matrix B. So this is B, this is P, P. Okay. And the second part will follow easily from the first, but it looks a little bit weird, but it's not that hard to prove, and we'll prove it in a second. B equals P transpose P to inverse times P transpose AP. So focus on this one. This is the key, and from this one we'll deduce the second one immediately. But the key thing is that you have an equitable partition. We'll see that these two things are equivalent, but for now the lemma says that equitable partition implies AP equals PB. Okay. So let's just prove this fact. Okay. So like I mentioned earlier, A is something big and it's indexed by the vertices, and P is a tall matrix. Again, here you have these x's, x1, xm, and here you have V. So when you get the result, what we will get as a result, we'll get something that is of this form. It will be indexed by V and it will be indexed by x1, xm. So that's the result in the matrix AP. And what would I like to look? I would like to look at some entry here in this matrix. Now that entry corresponds to a row and it corresponds to a column. The row, what is it? The row is a vertex of the graph, X, and the column corresponds to some of these parts, Xj, okay? So when I do the calculation, I will look in the matrix AP, and I want to look in the row X and in the column Xj. And I want to see what I find there. And I will do the same thing for the matrix PB. I will look in the row X and in the column Xj and see what I find there. Okay. So for now, we have this picture. So we do matrix multiplication. In order to find that entry there, what do we do? Well, we take the row X here in the matrix A, and we take the dot product with the column which corresponds to this vector Xj. That's what we do. So what is that going to be? Well, you see, in that dot product, everything is labeled by vertex of the graph. So it will be a summation over all y in V of what? Well, the blue entries from the graph, that's actually A times xy. And the entry from the other side will be what? Will be a P of y xj. Now, because A is the adjacency matrix, it's the same thing as before. The only AXI that survive are the one that those Y's that are adjacent to X. So that's going to be summation over all Y adjacent to X. So that gets rid of the blue AXY of P of Y XJ. But now P of Y XJ, what are the values there? That P equals 0 if Y is not in the set XJ, but it equals 1 if Y is in the set XJ. So the only Y's that survive are the ones that are inside XJ. So in this summation, what are we counting? We are counting all the neighbors of X that live inside XJ. So this will be the cardinality of the neighborhood of X that is inside XJ. Okay, so what is this value? Well, this X came from the vertex. We pick an X, so we picked an X in V, and we picked a J between 1 and M. But because X is in V and we have a partition, X must be in exactly one of the sets, X1, X2, Xm. So let's just say X belongs to some Xi for some I between 1 and M. So what we get here is going to be Bij, because this is an equitable partition. Okay. All right, so I'll be quick, so I'll finish the other part now. I'm a bit over time, I'm sorry. So when we do the other expression P times the matrix B like this, we'll do the similar part. So here we want to, well, this result will be a tall matrix, and it's indexed by V, and it's indexed by X1, blah, blah, Xm here. There's X1, Xm here, X1, Xm, and V here. So we do the same, we take a X here, but we do the dot product of the row of the matrix P with the column Xj here. Okay, that's how we get this entry here in the position of Xj and X. And when we do the calculation, it will be what? It will be, so this entry here, it's a summation over L from 1 to M, because we're summing from all these entries here, and they correspond to 1 to M, of what? It will be of Px XL times, on the other matrix, what do we get? We get BLJ. And now this is a different type of sum, and which one survives? Well, the P's of X and L, there's only one of them that is 1, is the one that corresponds to the index L, where X belongs to that set. But that L is exactly this vertex I, this index I. So we get that, we get Px Xi times Bij, which gives us Bij. So this entry here, it's the same as this entry here, and it proves that AP equals PB. All right, so I will stop here, and what we'll do next time, we will show that from this equation, we can, the result that will prove is that if the partition is equitable, the eigenvalues of B will be eigenvalues of A, and we can use the small matrix B to get to the eigenvalues of A. And we'll also prove something about the eigenvectors of the big graph. They can be split according to whether or not they're constant on the parts of B, or if they're perpendicular on the characteristic vectors of B. Stop here.